Hello friends, welcome you all. So in this video, we will see some convergence related to regular expressions, and first I will show you the details about various convergence, and then one by one we will discuss all these convergences. So friends, for every regular expression, there exist equivalent finite automata as well as reverse is also true. For every finite automata, there exists equivalent regular expression. So I will tell you the relation between these regular expression and finite automata, and then we will see the different conversions for the same. So first, if I take this regular expression here at the top of this, so there is one circular relation, like this regular expression can be converted into NFA, with epsilon move, and then this regular NFA with epsilon move can be further converted to NFA without epsilon move, and then this regular this NFA without epsilon move can be converted into DFA, and again this DFA can be converted back to regular expression. So this become there is one circular relation between a regular expression and finite automata. So these three are different types of finite automata, and these are regular expressions. So all these conversions we will see one by one. So in previous video we have already seen NFA with the epsilon move to NFA without epsilon move conversion, and NFA to DFA conversion we have already seen in some previous videos. The link of these videos will be available in comment section. Now some DFA to regular expression conversion we will discuss, and regular expression to NFA without with epsilon move conversion we will discuss. So sometimes, my friend, you can always see, as DFA can be converted into regular expression, so regular expression can also be converted directly into DFA. So this is another way. Regular expression can be converted into DFA by this path, but there is one more method that directly convert regular expression into DFA. That method we will also discuss. So here in this video, I will start with this conversion. So in this video, I will start with this conversion, DFA to regular expression. So first we will start with finite automata to regular expression conversion, and for this purpose, my friend, we will use one Arden theorem that is called as Arden's theorem. As this was proposed by Arden, so it in the name of him, it is called as Arden's theorem. And what this theorem says, that we will discuss. So according to Arden's theorem, if P, Q, and R are three regular expressions, and these are related to each other, like with the relation R equal to Q plus R into P, RP, Q plus RP, then we can write directly as R equal to QP star, or you can say Q dot clean closure of P. So if you can find this relation between three regular expressions, so you can directly write it like this. So there is one proof for this Arden's theorem also, so that we will also discuss. So like see, that proof we can create from this relation itself. So if I place R equal to Q plus RP here, see, R equal to Q plus RP, Now, in place of this r, if I replace it with r equal to q plus rp, then it will become q plus r into p, r into p, q plus r into p. Then you can say it as, you can rewrite it as q plus qp plus rpp, rpp. Then again, if I replace this r with this relation, using this relation, so we can rewrite it like this: r equal to q plus qp plus q plus rp p p, like this. Q plus rp p, like this. So you can see, my friend, here, if I rewrite it like this: q plus qp plus qp is p, qpp. If we open this bracket, so it will become r into ppp, ppp, like this. So now you can see, my friend, if we continue to do the same for infinite number of times, so it will become r equals to qp, q plus p, sorry, it will become q plus qp plus qpp plus qppp triple p plus, like this, any occurrences of p, any number of occurrences of p. Now if we take q as a common, now if we take q as a common, so we will get q in common, and then epsilon plus p plus pp plus ppp plus. Now you can see, my friend, this particular set, you can replace as, see, it is including epsilon and all, see, these plus representing choices. So you can select here epsilon, you can select here p, you can select here pp, you can select here ppp, or you can select any number of occurrences of p. So that means you can rewrite, it is clean closure of p. It is nothing but it is clean closure of p. So if you can find three regular expressions connected with each other or related with each other like this, so you can directly write r equal to qp star. So now this was the mathematical proof of Arden's theorem, and now we will see the use of this Arden's theorem to convert finite automata into regular expression. So friends, this FA can be any NFA, can be any DFA. So I will take two examples of these conversion to explain. One, I will use NFA to regular expression, and then I will use DFA to regular expression. So you can see, my friend, here I can take one regular NFA first. So suppose this is the given NFA, it is Q0, then any 0 comma 1 for both self loop is there, and then 0, then Q1, and then Q2. One more state is there, Q2, which is final state. So this would be 1. So suppose this is this is uh, NFA. This is the given NFA, and we need to convert this NFA into regular expression. So you can see, my friend, how what kind of language this particular NFA is representing. So you can see this is the initial state, and in initial state we have self loop of 0 and 1 both. That means we can have any number of zeros and ones. So it will show, it will represent any combination of zeros and ones. Then followed by on Q0, if we are getting N0, so we can move to Q1 also. And then on Q1, if we are getting a 1, so we can move to Q2, which is final state. So in this particular NFA, you can see initially we can have any combination of zeros and ones, but the ending must be with 0 and 1. So this particular NFA is representing machine to accept all binary strings ending with 0 1. So let's see how we can find a regular expression for this. So you can see, my friend, for this we will write equations for all the states of NFA. All the states of NFA. So first we are writing for Q0. We are writing for Q0. So now how we write equations? So in for writing equations for any state, we need to identify how we can reach to that particular state. How we can reach to that particular state. So now as Q0 is initial state, so obviously without any input we can reach to Q1. So Q0, sorry. So I can use epsilon. Without giving any input, we can move to Q0 as it is initial state. Then one more choice how we can reach to Q1. If we are giving 0 on Q0, then we can also move to Q1, Q0. So on Q0, if we are if we are applying 0, so we can move to Q0 again. Now one more choice is there. Either we can have 0 on Q0 or 1 on Q0. So again I can write as Q0 dot 1. Q0 dot 1. So this is the way how we can create the equations for any state. So now this on Q0, there are three ways to reach Q0. First is epsilon without taking any input, as it is the initial state. So without taking any input we can be in Q0. So I have mentioned this. Then on Q0, if we are applying 0, so we may stay on Q0. So this is another way of reaching Q0. Then on Q0, if we are giving 1, so again we can stay on Q0. So this is another way of reaching Q0. So now these are the three different ways to reach Q0, and I have mentioned all these three ways with the plus operator to show the choice between these three. So now this is the equation for Q0. This is the equation for Q0. So I can write it as equation 1. Then on for Q1, I can write another equation like, now what are the different ways to reach Q1? So according to this NFA, only applying 0 on Q0, we can reach to Q1. So there is only one way to reach Q1, and what is this? On Q0, if we apply 0, then we can move to Q0, Q1. On Q0, if we apply 0, then we can move to Q1. Now, this is equation 2 for Q1. Now, on Q2, how we can reach? So, now we can write equation for Q2. So, on Q2, there is only one way to reach Q2, which is on Q1, if we apply 1, then we can reach to Q2. So on Q1, if we apply 1, so we can reach to Q2. So that means we can have these three equations for all three states. All three states. These three equations for all three states. Now, on in we can rewrite equation of Q0 like this. You can see here it is epsilon, here it is Q0, here it is Q0. So we can take Q0 common from these two expressions. So now what we will get, so it will we will get Q0 equals to epsilon plus Q0, which is common, and 0 plus 1. 0 plus 1. 0 plus 1. Now you can see, my friend, this is something like R equal to QP is R equal to Q plus RP. So you can consider as R as Q0. You can consider epsilon as Q. You can consider Q1 again as R, Q0 again as R, and you can consider 0 plus 1 as P. 0 plus 1 as P. So now this is the form of R equal to Q plus RP. Now, if this form is there, so we can write R equal to QP star. R equal to QP star according to Arden's theorem. So now, if we rewrite this as this, so we can have Q0 equals to epsilon dot P star. P is here 0 plus 1. So 0 plus 1 whole asterisk. Clean closure of 0 plus 1. Now moving C dot with epsilon, that again Q0 means it will have 0 plus 1 whole asterisk. That means clean closure of 0 plus 1. So this is the value of Q0. This is the value of Q0. Now put this value of Q0 in Q1. Put this value of Q0 in the equation 2. So you will get Q1 equals to 0 plus 1 whole asterisk dot 0 dot 0. Now this particular value of Q1, this particular value of Q1, you can place into equation 3. You can place into equation 3, and by doing this, you can find out the value of Q2. So now Q1 dot, this is the value of Q1. So here we can write as Q1 as 0 plus 1 whole asterisk dot 0, then dot 1 dot 1. So this is the final value of Q2. This is the final value of Q2. And my friend, as Q2 is the final state in this NFA, as Q2 in the final state in this NFA, so whatever value of Q2 we are finding, that would be the final regular expression for this machine. Final regular expression for this finite automata. So for this finite automata, the regular expression would be 0 plus 1 whole asterisk dot 0 dot 1. And you can see, my friend, what this is representing. It is representing 0 plus 1 clean closure of 0 plus 1. That means any combination of 0 and 1 followed by 0 and 1. Followed by 0 and 1, which is the language of this NFA. So this regular expression is for this NFA. I hope it would be very much clear. And if you have still any doubt, you can always write to me in comments. Now we will see one more example where I will take DFA regular expression conversion. This was NFA to regular expression conversion. Now I will take one more example where we will convert DFA into regular expression. So friends, this is another example where I have taken DFA and I will convert this DFA into regular expression, and the language of this DFA is same as the NFA that we have used earlier in previous example. So it will also accept all strings of 0 and 1 ending with 0 1. So you can see the different transitions here, and this is the DFA. So now I will start converting this DFA into regular expression, and the process is same. So I will start writing equations for each state. So I will start with Q0 as it is initial state. So I can write equation. So now how many ways are there to reach Q0? So as it is initial state, so I can use epsilon to reach Q0 without giving any input. Then on Q0, if we are applying 1, so we will reach again to Q0. So on Q0, if we are applying 1, so I can reach to Q0. Then on Q0, on Q2, if on Q2 if we are getting 1, so we can move to Q1, Q0. So I can write Q2 dot 1 again. So these are the three different ways to reach Q0. Now I will write another equation for Q1. So what are the different ways to reach Q1? Now on Q0, if we are applying 0, so we can reach to Q1. So I will start with Q0 dot 0 plus another way of reaching Q0 is on Q1, sorry, reaching Q1 is on Q1, if we are applying 0, so we can stay on Q1. So I can write it like this. Then on Q2, again we are applying 0, so we are moving to Q1. So on any state, if we are applying 0, so we will move to Q1. Now this is the equation for Q1. Now again I can write one equation for Q2. Again I can write one equation for Q2, and which is C. So how we can reach to Q2? So we can see it from here. On Q1, if we are applying 1, then we can reach to Q1, Q2. So on Q1, if we are applying 1, so we can reach to Q1, Q2, sorry, we can reach to Q2. And this is the only way to reach Q2. Now, these three equations are there for each state. Now we can start solving these states. Now we can start solving these states. Now you can see, my friend, if I make it equation 1, if I make it equation 2, and it is like equation 3, then I can solve these three equations. How? See, we can put this value of Q2 from equation 3 in equation 2. We can put this value of Q2 from equation 3 in equation 2. So we will get, so we will get, so we will get Q0, sorry, Q1, Q1 equals to Q0 dot 0 plus Q1 dot 0, Q1 dot 0 plus Q2. In place of Q2, we are putting Q1 dot 1. So it will be Q1 dot 1, and dot 0 is already there, so dot 0. So this is the new equation for Q1. Now here In these two terms, q1 is common. So we can take it common. So we can rewrite it like this. q1 equals to q0 dot 0 plus q1 taking common. So this will be 0 plus 1 0. 0 plus 1 0. Now you can see, my friend, again it becomes in the form of r equal to q plus rp, where this is r, this complete is q, plus this is again r, and this is again p. So now if this is the relation, then what we can write? R equal to qp star. R equals to qp star. So now we can write q1 equals to q1 equals to q q0 dot 0 q0 dot 0 dot p star. P, what is the value of p here? 0 plus 1 0. 0 plus 1 0. So 0 plus 1 0, clean closure of 0 plus 1 0. 0 plus 1 0. So this is the value of q0, q1 in the form of q0, in the form of q0. Now we can put this value, here in q2, here in equation 3, here in equation 3. So we will get the value of q2 in terms of q0. So from it, we can consider this as equation 4. So from equation 4, we will put the value of q1 in equation 3. So q2, putting value of value of q2 q1 sorry q1 in equation 3. Now this value, if I put there, so q2 becomes q2 is equals to q1 dot, sorry, q0 dot 0 dot 0 plus 1 whole asterisk dot 1 dot 1. So this is the new value of q0, sorry, q2 in terms of q0. We can consider this as equation 5. Now see, my friend, if I put this value from equation 5 in equation 1, so I will get here, what I will get here, you can see, putting value of q2 in equation 1, so we will get new value of q0 as q0 equals to, I can write here, q0 equals to epsilon plus q0 dot 1 plus q2 dot 1. Now the value of q2 is q0 dot 0 dot 0 plus 1 0 asterisk dot 1. So this is the new value of q0 in terms of q0 itself. Now this these two expressions having q0 in common, so we can take it as common. So we can write it like this: q0 equals to epsilon plus q0 1 plus 1 plus 0 1 sorry 0 dot 0 plus 1 0 whole asterisk dot 1 dot 1. So now again, my friend, you can see this is the form of r equals to q plus r into p. R equals to q plus r into p. So now what is so if this is the form, we can write r equal to qp star. So now here I'm writing it here. I'm writing it here. So q0 equals to q means epsilon. So if we merge epsilon with anything, it will we will get the same expression. So this would be the clean closure of this complete expression. So this would be 1 plus 0 0 plus 1 0 asterisk 1 dot 0 dot 0. So I hope, friend, this would be very much clear to all of you. Like what is the how we get the value of q0 here. Now, as you can see, my friend, q2 is our final state. Q2 is our final state. So we need to get the value of q2 to find the final regular expression for this machine. So now we have q0. So now putting this value of q0 here, putting this value of q0 here, we can get the value of q1. And then putting this value of q1 here in this expression, we can get the value of q2. We can get the value of q2. So now I'm directly writing the value of q2. So now q2 will be, this you can consider as equation 6. This you can consider as equation 6. Now I will write directly the value of q2. So you can see, my friend, q0 is this. And again I'm writing it like this. 1 plus 0, 1 plus 0, 0 plus 1 0 asterisk 10 dot 1 whole asterisk, whole asterisk. Now this is the value of q0. Then for finding out the value of q1, we need to add this expression with this. So we will add dot 0, then 0 plus 1 0 asterisk. So this becomes the value of q1. Now in value of q1, if we put another one, so it will become the value of q2. So we can put one value dot 1 here, dot 1. So this is the final value of q2. This is the final value of q2, and this is the final regular expression for this particular machine or particular DFA. Now you can have some questions like, this is not looking like 0 plus 1 whole clean closure and dot 0 dot 1. That means it is how it is representing the all binary strings ending with the 0 1. So let me clear, my friend. You can always write two regular expression for same language. You can always write two regular expression for same language. So if you see it closely, then you will find this is representing the same language. I will explain it. See, the clean closure of this whole will generate any combination of zeros and ones. Any combination of zeros and ones. So this is also required in this DFA. So at first we will get any combination of zeros and ones. Now, my friend, if this becomes epsilon, as it is clean closure, so it may become epsilon. If it is become, it is epsilon. If it is epsilon, then you will have 0 1 at the end. 0 1 at the end. That means it will end with 0 1. Now suppose if it is not epsilon, then if you consider this 0 as first symbol and this 1 0 as another symbol, so in any combination of this particular expression, either 0 would be there at the last place or 1 0 would be there at the last place. So if 0 is there at the last place, so this would be 0 followed by 1. Now, if 1 0 would be at the last place, so again you can see 1 0 followed by 1. That means again they are ending with 0 1. So that means this regular expression is nothing but it is the combination of any combination of zeros and ones ending with 0 1. So I hope, friend, this regular expression is very much clear to all of you. And if you have any doubt, you can always write to me in comments. And I hope this will clear all doubts regarding Arden's theorem. So friends, till now we have discussed both the example in this video where we had only one final state. Now if you have two final states in any finite automata, then how to get regular expression for this? So in this and this is NFA, and in this NFA you can see we have three states, and out of these three states two final states are there, which are Q1 and Q2, sorry, Q2 and Q3. Now I have written equations for all these states. So on Q1, what are the different ways to reach Q1? So as it is the first state or initial state, so we can use epsilon to reach Q1, and then on Q1 if we are applying 0 or 1, that we will reach to Q1 only. So these three ways are there to reach Q1. So this is our first equation for Q1 state, and then on for Q2 only one way is there to reach Q2, which is applying 0 on Q1, so we will reach to Q2. So this is the equation for Q2, as well as the equation for Q3 is how we can reach to Q3 by applying 1 on Q2, we can reach to Q3. So these three equations are there for each state, and in this machine you have two final states. So now we will solve these equations and we will try to find out the regular expression for this NFA. Now if we rewrite the equation 1, then we can take common expression from these two expressions. So Q1 is common, so we can take out of these two expressions we can take Q1 as common. So now it can be rewritten as it can be rewritten as Q1 equals to epsilon plus Q1 in common, and in brackets 0 plus 1, 0 plus 1. So now my friends, you can see this is the form of R equal to Q plus R into P. Q plus R into P. So here we can write Q1 equals to epsilon, which is Q, dot 0 plus 1, which is P, clean closure of 0 plus 1. Clean closure of 0 plus 1. So we have the value of Q1 as clean closure of 0 plus 1. Now we can put this value of Q1 in this equation Q2, equation of Q2. So now we can get the value of Q2 as 0, clean closure of 0 plus 1 dot 0, as this 0 is there. So we will place 1 0 here at the end. So the expression of Q2 would be 0, clean closure of 0 plus 1 dot 0. So this is the value of Q2. Now putting this value of Q2 in equation 3, so we will get the value of Q3 as 0 plus 1 whole asterisk, or you can say clean closure of 0 plus 1 dot 0 dot 1. So this would be the value of Q3. This would be the value of Q3. Now, friends, as we have two final states in this NFA, so to get the final regular expression for this NFA, we need to add, we need to provide two choices of final states. So as we have two final states here, so we can get the final state by uh, getting a union of expression of Q2 and Q3 both. So now the final regular expression would be 0 plus 1 whole asterisk, or you can say clean closure of 0 plus 1 dot 0, which is the value of Q2. And then we apply 1 plus operator here, and then clean closure of 0 plus 1 dot 0 and dot 1. Clean closure of 0 plus 1 dot 0 dot 1, which is the value of Q3. So by providing these choices, we can get the final regular expression for this machine. Now, in this the same logic you can apply, or same concept you can apply for the any number of final states. Any number of final states. If more than one final states are there, then you can add expressions of all final states with plus operator, and you can get the final regular expression. I hope, friends, it would be very clear to all of you. And still, if you have any questions, you can always write to me in comments. I will definitely reply your comments. Thank you. Thank you so much.